Hi, everybody. All right, here we are, ready to dive back into section 3.2. Probably, yeah, definitely 3.3 today, and maybe even a little bit of 3.4, because the chain rule doesn't even show up until 3.4, technically. But where we left things off during the last class was we talked about differentiable functions in 3.1. And then we wanted to increase the number of functions that we can take the derivative of without the limit definition. And so in 3.2, we were looking at things like the constant rule, the positive integer power rule, the constant multiple rule, and then the sum and difference rules. And those four together basically give us the power to differentiate polynomials. The other ways that we can combine two functions other than sum and difference would be the product rule. And we did look at the product rule. That's a good summation of the product rule. And remember, that was based on thinking about areas and kind of the distributive property. And the last big one that was mentioned in the video that we watched, visualizing product and chain rules, was the chain rule. And we're eventually going to get to that. Chain rule's down here. But where we're actually going to, start is where we left off. At the product rule, we implemented the product rule once here. Yeah, and if you wanted to pause and do any of those, that would be fine. But yeah, we're actually going to take a look at the quotient rule coming up soon, because quotient is division rather than multiplication, and it deserves its own rule. Okay, so before we get to the quotient rule, this part is called the reciprocal rule, and I would call this thing a lemma. A lemma is a thing in mathematics that's like a little theorem, but a little theorem proven so that when you get to prove the larger theorem, your job is easier. So this is like a stepping stone. The reciprocal rule works for the reciprocal of a given function g. In practice, this is not one that you're going to want to necessarily memorize, but the proof of this is going to be a nice stepping stone when we look to the proof of the quotient rule. So yeah, thought I'd throw that out there. A little fun fact. I would call this a lemma. The proof is just going through the steps of the limit definition of the derivative. We've done this kind of thing where we're working with probably the function 1 over x. I think we did that on our activity, where we had to make common denominators on top and figure things out. But yeah, in the end, what you get is the derivative of g on top, I guess with a negative sign, and 2 copies of g on the bottom. So that's kind of cool. That's a reciprocal rule. Don't worry about memorizing it. But it's going to make the proof of the quotient rule, which is something that we actually do want to memorize, a lot easier. It makes the proof like that short. But yeah, here we have the quotient rule, and there's a lot of symbols going on. And yeah, the way that I still remember the order of which thing gets a prime and which one doesn't is still the same thing I learned in high school, which is low d high minus high d low all over low low. um, but yeah, all that means is low is standing in the place of g because that's on the bottom of the fraction, and high is standing in the place of f. So d high would be the derivative of f, and d low would be the derivative of g. And notice that I've got this as going g f prime rather than f prime g. Not a big deal. That's just the commutative property of multiplication. But for some reason, low d high minus high d low all over low low is kind of a useful mnemonic device to remember the quotient rule. It's almost like the product rule on top, except there's a minus sign. And it's important because there's a minus sign that you take the derivative of the numerator first and then the derivative of the denominator second. So if you don't want to use this, you can figure out your own way to memorize the way that the quotient rule works out. But yeah, once we have the quotient rule, which again can be proven pretty quickly once we know the reciprocal rule, because all we do is apply the product rule between f and 1 over g, and we're able to find the derivative of 1 over g pretty quickly because we've already got the reciprocal rule going on. Then you make common denominators again. So you're multiplying this by g of x over g of x, and eventually you get the quotient rule. So yeah, we need to use the limit definition up here and down here. Since we already did that, we've got it. Cool. So we could use the quotient rule on one of these examples. I think right now I'm going to choose A, just because B and C are a little bit crazy with the number of fractions. So I'd rather, our first try be one where it's reasonable. But yeah, remembering that, we would label the top function as f and the bottom function as g. Yeah, the derivative of that would be the derivative of f times the derivative of g minus, the f times the derivative of g all over g times g on the bottom. And then, filling this out, we would go, the derivative of the numerator would be 10x plus 1. The denominator just remains itself, x squared plus 2. We're subtracting then f, which is 5x squared plus x, and the derivative of the denominator, which is 2x. And that's it, because the constant 2 just goes to 0. And then in the denominator, we've got g times g, which is x squared plus 2 squared. And again, since we've completed the quotient rule, we found the derivative. And everything else that we would do after this point would just be cosmetic. And I guess if we're not going to, simplify things, I could do another one. Let's look at C real quick. All right. Or, and feel free if you want to try C before me and then resume this, feel free to do that. But yeah, all right, I'm going to do it. Yeah, we would take the derivative of the top and for that first term, we would have 1 over 2 times the square root of x. Again, that's the power rule in play. Plus, we would have, this one is 2 times x to the negative 1/2. So we would bring down the negative 1/2 and we would get negative 1. So actually, oh, hold up. I'm going to change this to a subtraction sign. But then the power on that would be negative 3/2. So yeah, we'd have x to the negative 3/2 there. And that's just the derivative of the top. Then we would have the square root of x for the bottom. We would subtract the top, which is just itself. Times the derivative of the bottom. And the derivative of the bottom will be 1 over 2 square roots x all over the bottom squared, which is, the square root of x squared. Well, that's nice. That'll turn into just an x. But again, you could, multiply this out and probably simplify things so that it would look nicer. But this is the new part, the hard part, implementing the quotient rule. All right. Let's keep going. So that's the quotient rule. And the next one, we've seen it before, but we'll remind you of the chain rule. The chain rule happens when you have a composition of functions. And remember in the video, there was like a few number lines. In the video, there was an X number line, there was a G number line, and an F number line. And what we were imagining was that, I don't know, there was some little change in the input of X. And I don't know, maybe we give that a direction. Yeah, I don't know, yeah, it's horrible. All right, so we nudge X a little bit in a certain direction. And the idea is that this nudge in the input induces a nudge in the intermediate function. You know what? I'm going to use purple. And we could call this dg. But we realize that dg is going to be some function of dx. And then finally, there's some df that's induced by that. So you change the input, that causes a change in the intermediate function, and then that causes a change in the outer function. And that's the idea that we've got going on with the chain rule. This first part, let's call this, well, I don't know what color I want to use here. It doesn't matter. But this f prime of g of x part, that is the rate of change of f with respect to g of x. So let's say rate of change of f with respect to g of x. And this part you can think of as this arrow. Like, I guess it's the coordination of dg and df. Maybe, yeah, I'll I'll take the risk and I'll kind of box that arrow in to highlight it. But another way to write this would be DG, or sorry, DFDG. Good grief. And here, if I'm doing a good job, might as well go the whole way and be consistent with my colors. We got this. All right. And this is the same DFDG that you see down here. So this whole factor, it's the rate of change of f with respect to g of x. We would label that as DFDG in alternate notation. And it's really describing the rate of change between df and dg. And then the other one, which, you know, you've probably figured out by now, we've got, this is just the rate of change of g with respect to x. Ugh, sorry, that was horrible. And the fraction that we would be looking at here between the differentials would be dg on top and dx on the bottom. But yeah, we would be looking at the coordination between dg and dx there. Okay. So yeah, we will use both of these notations when convenient. But yeah, the idea is a small nudge to x causes a nudge in an intermediate function g, which in turn causes a change in the overall function f. And we can, you know, shorten that as df dx, where the small nudge to x eventually causes a nudge to the overall function f. So yeah, chain rule. And gosh, I guess we'll get to some good examples of that later when we actually get to 3.4. But we'll be able to pretty quickly jump into the examples when we get there, because we've done this hard work. And I guess one of the things that, if all of this notation is just looking crazy right now, one of the things that I wrote down here at the bottom was just like kind of a conversion factor. If you wanted to think about this as kind of converting between units almost, you know, one way to find out that there is 5,280 feet in a mile. Let's pretend that we don't know that for a second. We're wondering, how many feet are in a mile? Well, if you know how many yards are in a mile and how many feet are in a yard, you can multiply those rates together. They're, you know, conversion factors, but yeah, you can think of them in a similar kind of way. But yeah, when you multiply those together, just like the DGs match up here, the yards would match up here, and those would cancel, and you'd be left with the units of feet per mile. So yeah, I thought that was maybe a little bit more concrete. Cool. All right. Section 3.3 is labeled derivatives of trigonometric functions. And I, you know, copied down the formulas. These are the 6 that, as of now, you would want to memorize. And yeah, these are ones that are good to have in your back pocket. One of the ways to remember which way the signs go is that if the original function that you're starting with starts with a c, so cosine, cosecant, or cotangent, the derivative ends up changing the sign. So negative sine, negative cosecant, cotangent, or negative cosecant squared. Yeah, these are things that it would be good to memorize. And there's a couple different ways of understanding how these come about. The first way, now I didn't make this one, Dr. Jack L. Jackson II made this. But it was a nice, just, yeah, something that was nice and already made. But yeah, here's our sine function. And if we wanted to come up with the derivative for the sine function, we could use the limit definition. And this is what the limit definition looks like. You have to use an angle sum formula to split apart the original sine of x plus h, and you get this mess. And then you have to keep using trig identities along the way to eventually get to a spot where you can substitute in the limit as h goes to 0 on both of those. And those are kind of ugly in themselves, but we could do those to eventually figure out that you get cosine of x in the end. So just using the limit definition on our original function is one very valid way to understand what the derivative actually is. And so very similar differentiation or derivations for cosine. We got that angle sum thing going on again. We end up getting minus sine in the end. Tangent. Here we split it up into sine and cosine and use the quotient rule. Quotient rule is actually what's going on here. No limits involved, since we already know the derivative of sine and cosine. So that's kind of cool. End up getting secant squared. Cosecant, that is the reciprocal of the sine function. And so, yeah, you could even maybe think of using the reciprocal rule here. But yeah, same thing. For cosecant, secant, cotangent, there are derivations that, can be done to figure out each one of those. And that's kind of cool to check out. Oh, geez, that one's over there. But yeah, that's one way that you can kind of tackle figuring out the derivatives. The other one, we looked at the derivative of sine in a geometric sense in that last, here we go. In that video that we watched on Thursday. But here's another thing that I actually did make. Here's just a unit circle. And on this unit circle, we've labeled cosine, sine, tangent, cotangent, cosecant, and secant in terms of, where these trigonometric ratios actually appear geometrically. And so, yeah, I think that's kind of cool. And one of the things that you could do geometrically is take whatever our theta value is and nudge it just a little bit. So, yeah, I turn all these things on there, but nudging the angle theta would nudge us around the edge of the unit circle, d theta units. So the angle changes by d theta, the arc around the circle changes by d theta. And just that little nudge gives us a bunch of changes in the cosine, sine, everything else. Notice that, in this first quadrant, when you nudge this point ahead by d theta, your x value becomes less. And so the d cosine, this differential, points left in a negative direction. And in a way, that's one way to make sense of why we see the derivative of the cosine having an opposite sign when this happens. So cosine is getting smaller, the cosecant is getting smaller, the cotangent is getting smaller because that's that green length up there. So cotangent, cosecant, and cosine, cosecant, and cotangent are all getting smaller. And tangent, which this one's shooting up here, sine and secant, all of those lengths are growing when you just increase theta by just a tiny bit. You nudge that value around, it makes the x value smaller, makes the y value bigger. This part gets bigger over here. This cosecant part gets smaller, cotangent gets smaller, tangent gets bigger. And going into here, you could totally do similar triangles and figure out ratios and that kind of stuff, just like the video did. I did not have time to do that. This took me long enough as it does. But yeah, you could totally figure out the derivatives, probably using similar triangles, figuring out where theta shows up here and that kind of stuff. You can do it. And if you do want to do that and show it off to the class, I would give you bonus points, like so many, like at least 5. If you wanted to show something cool like that. Anyways, figuring out a derivative using differentials. Anyways, let's get back to this. So you can use the limit definition of the derivative to figure out what these formulas are. You can also use geometry to get an idea of what these values should be. And then I think we've got one last example. This section 3.3, not the greatest examples in the world, kind of obscure stuff that I don't think is too important. But we will try example number 5. And here we're going to be doing some simple harmonic motion with a mass hanging off of a spring. So this is all blah, 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 restoring force. Suppose an object of mass m is hanging on a spring and is at equilibrium. If we pull downward by 50 centimeters and release it, the equation of motion is given by negative 0.05 cosine of t. And our function's y of t. That's fine. Where y is the vertical distance from the equilibrium measured in meters with an upward displacement considered positive, and t is measured in seconds. Cool. I'm gonna just scoot this over a little bit so we have some room to write over here. But yeah, let's just go A through D real quick and try to get some short answers to this. Here we go. All right, part A. Find the position at 10 seconds. Well, we're already given a position function. It's y of t. So all we're finding is y of 10, which would be negative 0.5 cosine of 10, which, oh, I think this works out to be something like 49 or blah, blah. I don't know. It's in the book. Take the cosine of 10 and you're going to be great. That one's boring. Part B. What's the maximum displacement of the object and when does it occur? Well, since this is going up and down and we've pulled it down by 50 centimeters and we're not really accounting for any dampening of the motion over time. So we're ignoring air resistance, friction, all the other forces. I mean, this again is going to be just dependent on the cosine function that we have. We would be starting off at a minimum because we've pulled it down by 50 centimeters, and then we would get to a maximum pi units later, and then we would be down at a minimum once we get to 2 pi, seconds. So what's the maximum displacement? We would get minimums at I don't know, 0 plus 2k pi, where k is an integer. We would get maximums and yeah, I'm talking about we're above equilibrium when I say maximum, but that would just be pi plus 2k pi. And yeah, we would be 50 centimeters away from equilibrium in either case. Cool. The ones that I really wanted to look at were the derivatives here. So find the maximum velocity and position where it occurs. So if we wanted to find, I don't know, maybe we call this v of t, but we know that this is y prime of t because we're taking a derivative. We can use our new knowledge of trig functions to look at the cosine, take the derivative of the cosine, we get negative sine. And so we're gonna, change the negative sign that we have to a positive and get 0.5 sine of t for our position function. And again, to think about maximum velocity and position where that occurs, we would be dependent on the sine function. Sine's going to reach a maximum at pi halves, and then again at 3 pi halves, that would just be in the opposite direction. So yeah, so max pi halves plus multiples of 2 pi min 3 pi halves plus multiples of 2 pi. Cool. And we're going to see this on a graph soon. But, to do the maximum acceleration, we would, again, take another derivative. So maybe we call this a of t, and that would be y double prime. And so we're taking the derivative of what we got right there, 0.5 cosine of t, because the derivative of sine is just cosine. And the maximums here will be max at 0 plus 2k pi and minimums at pi plus 2k pi. Cool. Let's go ahead and take a look at the graph and see how this all goes, because I think it's pretty cool. All right, look at this. I even put a picture in the background. I'm going all out. Geez, and it's 4:27 on Friday afternoon. Yeah, so we've got a picture in the background. We are taking this mass, pulling it down 50 centimeters from its equilibrium position and letting it fly. So if I bring our, parameter back to 0, for t equals 0, basically, notice that I'm going to have an acceleration arrow in blue and a velocity arrow in red. And those arrows are based off of the height of each one of these functions. So we've got velocity in red. Notice that it's at a height of 0. And we've got acceleration in blue. Notice that it's at a height of, I guess, 0.5 here. So 50 centimeters per second upwards. But instead of looking at all those swirly lines at the same time, I think it makes a lot of sense just to create a couple of vectors. And these vectors, what I've done is given them no x component, so they don't go left to right at all, but I've given them a y component that's based on either the value of v of w or a of w whenever we change w along here. So when you've got the thing pulled down the whole way and you let go, it's going to be accelerating, but at that instant, it's not going to have any velocity yet. But yeah, let's watch this. I think I've got it going out to 4 pi. Whoa, okay, that's pretty fast. We'll slow it down for the next run. Boom. Okay, so we're getting some velocity. Here we get to the equilibrium point and acceleration gets down to nothing. Here we get to a maximum, so acceleration's coming back down. Maximum velocity happens at the equilibrium point. Maximum acceleration happening once things are pulled down, or I guess pulled up, depending on which way you want to think about it. But yeah, I don't know. I think that's a pretty cool thing to look at. We're doing calculus. Yeah, and those arrows, again, are based on the curvy things, but it's kind of ugly to look at all of those at the same time. All right. So that's cool. You're going to find waves like this all the time when you're doing engineering stuff. All right. So yeah, that's actually the last example that I wanted to do. Doesn't mean that you're allowed to go yet, because I would like you to watch this video about the number e, and specifically exponential functions when you're looking at calculus. It's a super cool video. Again, the animations are great. So I think this is a good way to go to, to introduce you to taking derivatives of exponential functions. So after you watch that video, we now have powers of taking derivatives of polynomials. We can take derivatives of trig functions. You will be able to take derivatives of exponential functions. We can take derivatives of products and quotients and compositions using the chain rule. We're going to get more practice with the chain rule coming up soon. But yeah, cool. Go ahead and watch that video. See you later.